Hey there, and welcome to this explainer. I am thrilled you're here. Today we are exploring one of the most fascinating and profound relationships in all of science, the delicate, invisible two-way street between electricity and magnetism. It's the underlying principle that literally powers our whole modern world. If you've ever wondered how the energy from a massive power plant makes it all the way to the tiny charging cable for your smartphone, you are in exactly the right place.
Here's our roadmap for today. We're going to start with the electricity-magnetism connection, move on to mastering magnetic fields, then see how magnetism actually creates electricity. After that, we'll pit motors against generators and wrap it all up with AC, DC, and transformers. Let's get into it.
All right, part one, the electricity-magnetism connection. So this whole macro concept, it really kicked off back in 1820. Hans Christian Ørsted was the guy who discovered the magnetic effect of current. He noticed something simple, but honestly completely game-changing. A magnetic compass needle physically deflected when it got close to a wire carrying a current. And get this, the direction of that deflection actually flipped if the current's direction changed. Electricity was, without a doubt, creating a magnetic field. That massive realization leads directly to a crucial piece of tech we use all the time, the electromagnet. Basically, it's just a temporary magnet you make by passing electricity through a solenoid. Now, if you're wondering what a solenoid is, it's literally just an insulated copper coil shaped like a cylinder with a bunch of tightly wound turns. The absolute best part about an electromagnet, unlike your standard permanent magnet, you can turn it off. Plus, you can perfectly tailor its shape and size for things like loudspeakers or electric bells.
So, if you're an engineer, how do you actually make these things stronger? Well, you have three main tricks up your sleeve. Number one, just increase the number of turns in the coil. More turns equals a beefier field. 2, crank up the magnitude of the electrical current flowing through it. And 3, slide a soft iron core right down the middle of the solenoid. These three simple modifications give us absolute control over the magnet's strength.
Moving on to part two, mastering magnetic fields. Let's visualize this. Picture a classic lab setup. You've got a flat, square piece of cardboard with a hole punched right in the middle, and a straight current-carrying wire going straight up through that hole. If you sprinkle some really fine iron powder on the cardboard and give it a little tap, the powder magically arranges itself into perfect concentric circles right around the wire. It's basically a real-life map showing us the exact circular shape of the magnetic field wrapping around that straight wire. But how do we figure out which way those circular fields are actually spinning? That's where Maxwell's right-hand thumb rule comes in. Seriously, hold up your right hand right now. Imagine you're gripping that wire. If your thumb is pointing in the direction the current is flowing, the way your fingers curl around the wire, that's the exact direction of the magnetic field. It is a wonderfully simple, completely foolproof rule. Okay, so what happens when we take that wire and coil it into a solenoid? The magnetic field suddenly looks a lot like what you'd see around a standard bar magnet. It's super strong at the ends and kind of weak in the middle on the outside. But inside that coil, the magnetic field is perfectly uniform. And since it acts like a bar magnet, one end naturally becomes a north pole and the other a south pole the second the current flows. So how do we spot the north pole? We use a slightly different version of our hand trick, Maxwell's right-hand grip rule. Hold that right hand up one more time. This time, curl your fingers in the direction the current is traveling through the loops of the coil. Wherever your thumb ends up pointing, boom, that is the north pole of your electromagnet. All right, so we've established that flowing electricity creates magnets. But this brings up a huge narrative-flipping question. If electricity can create magnetism, can a magnet create electricity? Is this invisible street actually going both ways? Let's find out in part 3, magnetism creating electricity. To wrap our heads around this, we really need to nail down the concept of magnetic flux. Denoted by the Greek letter phi, it's essentially the total number of magnetic lines of force passing perpendicularly through a specific area. Think of it like the total volume of magnetism pouring through a hoop. We measure this flux in a unit called Webers, named after the German physicist Wilhelm Edward Weber. Which leads us to a massive breakthrough, electromagnetic induction, defined by Faraday's laws. Here's the golden rule. Whenever there is a change in the magnetic flux linked to a closed coil, an electromotive force, or current, is induced in that coil. The strength of this current is directly proportional to how rapidly that flux is changing. But here is the kicker. The current only lasts as long as the flux is actively changing. If you just leave a magnet sitting perfectly still inside a coil,
absolutely nothing happens. You need motion. You have to change the flux.
Let's ground this in the real world with something like a bicycle dynamo. Inside one of these things, you've got a permanent magnet and a copper coil. When you pedal and the tire turns, it spins a little knob on the dynamo, which in turn violently spins that permanent magnet inside. Because the magnet is spinning like crazy, the magnetic flux hitting the coil is constantly shifting. That non-stop change induces an electric current in the coil, traveling right up the wire to light up the bike. Motion creates changing flux, and changing flux creates electricity. It's brilliant.
Let's compare applications in Part 4, Motors versus Generators. You know, a generator works on the exact same principle as that little bike dynamo, just scaled way up. It uses electromagnetic induction to turn kinetic, mechanical energy into electrical energy. If we want a generator to pump out even more juice, we have 4 main levers to pull. We can add more turns to the coil. We can boost the strength of the magnetic field itself. We can spin the magnet or the coil faster. Or we can shrink the physical gap between the coil and the magnet. Now flip that entire concept upside down and you get the motor effect. This rule says that if you place a current-carrying wire inside a magnetic field, the wire's going to physically move. This is the exact principle that runs the electric motors inside your fans, your hard drives, your washing machines. Instead of using physical motion to generate electricity, we take electricity and a magnetic field to force physical motion. To really lock in this inverse relationship, let's just put them head-to-head. Look at the energy swap. A generator takes mechanical energy and turns it into electrical energy. A motor does the exact opposite. Electrical energy becomes mechanical movement. Generators rely on electromagnetic induction, while motors lean on the motor effect. And generally speaking, generators use electromagnets to get the job done, while motors often stick to permanent magnets. They are literally 2 sides of the exact same coin.
And finally, Part 5, AC, DC, and transformers.
Before we talk grid power, we have to sort out the 2 main flavors of electric current. Take a look at that flat, steady line. That's direct current, or DC. Its magnitude and direction are constant. No surprises, just a straight shot. But then look at alternating current, or AC, with that crazy wave pattern. Its magnitude and direction are constantly flipping back and forth. That AC generator we talked about earlier? That's exactly what's pumping out this wavy, alternating current.
Since our massive power grids run on AC, we absolutely rely on a piece of genius hardware called a transformer. Operating entirely on electromagnetic induction, a transformer's job is simply to crank the AC voltage up or dial it down. It is insanely efficient. Basically, the energy you put in is the energy you get out. The secret sauce is that the voltage is directly tied to the number of turns in its coils.
Which brings us perfectly to the 2 main types of transformers. You have your step-up transformer, where the secondary winding has way more turns than the primary. This jacks up or steps up the voltage. We use these at giant power stations, so electricity can travel hundreds of miles across power lines without losing much energy. On the flip side, you've got the step-down transformer. Here, the secondary winding has fewer turns, which drops the voltage. You'll find these at local substations or literally inside that little charging brick for your phone, dropping a lethal 220 volts down to a completely safe 5 volts.
So that wraps up our look at this invisible 2-way street. From Ørsted's tiny compass needle deflecting on a desk, to the massive spinning turbines at a hydro plant, all the way down to the tiny step-down transformer keeping your phone alive right this second, it's everywhere. I want to leave you with this. Take a look around you right now. How much of your entire modern life relies totally on this delicate reciprocal dance between electricity and magnetism? Because honestly, without it, our world goes completely dark. Thanks for hanging out with me for this explainer. Keep learning and stay curious.